Hi guys. So today we're going to continue discussing intractability. Last time we defined the complexity classes of P and NP. In order to define these complexity classes, we had to come up with an abstract notion of a problem. This was represented by something called a efficiently computable binary relation. Complexity class P was all decision problems related to these relations that can be solved in a polynomial time. Whereas the class NP was all relations whose decision problem, or rather all relations that are efficiently computable. Namely, there is an algorithm that given an instance and a witness decides in polynomial time if the witness is a valid kind of solution to the instance. We introduced the notions of NP hardness and NP complete. Remember that these are distinct. NP hardness says that everything in NP reduces to it, and NP complete additionally requires the problem to be inside NP. Okay, it is possible for a problem to be NP hard and yet be outside of NP. We exhibited one NP complete problem, CSAT, circuit satisfiability, and then proved that a special case of it, Boolean satisfiability, remains NP complete. The plan for today is to additionally simplify the problem SAT, so Boolean satisfiability, to make the formula not even a general formula, but a formula with structure. We'll prove that it remains NP complete. And we'll build off of this very simple NP complete problem to show that other problems that may a priori not look like they have anything to do with NP completeness, in fact, are NP complete. Okay? So the first plan is we're going to define the simpler case of SAT. So let me first remind you what is SAT. SAT is the binary relation consisting of Boolean formulas and satisfying assignments. Okay, so phi, make some more, I'll write it here, such that phi is a Boolean formula such that phi of a equals 1. Okay, so remember this was the instance and this is the witness. Okay, so from last time we proved that SAT is NP complete. SAT is clearly is an NP because I can check this relation. I can check this condition given phi and a in polynomial time. In fact, I can do it in linear time. And moreover, this relation is NP hard because we reduced from CSAT. Given a subroutine that decides SAT, we were able to decide CSAT. So now we're going to discuss a slightly simpler problem called 3SAT. Okay, it is almost the same, where we're going to impose some structure on phi. So we're going to say that phi a itself is in SAT. Okay, so we have a Boolean formula, we have an assignment. Okay, and the Boolean formula is going to have some structure. So we're going to say that phi is a 3CNF. What does that mean? It is in conjunctive normal form, and each clause has 3 so-called literals. So what does 3NF mean? Let's just go through it as an example. For example, it may look like it's an end. So let me first say, at high level, it means that it is an end of ORs with each OR involving 3 literals. So for instance, you may have something like x1 or x2 bar or x3 and not x1 or x7 or x8 bar and right? So it is an end of ORs, and in each OR clause there are 3 literals. What is a literal? It's either a variable or its negation. Okay? So I am making the problem more structured I am restricting the type of Boolean formula that you are asked to decide. So this problem can only be easier than the original problem, right? Because it is a special case of it. But despite being a special case of it, now we'll prove that 3SAT is NP-complete. And this is particularly interesting because probably in some homework, or certainly it's explained in the book, you may have come across with the fact that 2SAT is in P. And so in particular, we do not believe that it is NP-complete. So notice that it's not, you cannot just, it doesn't follow logically that if you consider a special case of a problem that is NP-complete, the special case itself may be NP-complete also. It could be that the additional structure lets you do things that you couldn't do against general instances. And indeed, in the case of 2SAT, there is a polynomial time algorithm to decide whether there is an assignment. In fact, you can find assignment as well. Yet, with an end of ORs, where the ORs are 3 literals, actually turns out to be NP-complete. It's a bit of a sharp kind of transition. You go from P to NP-complete. Okay? So that's pretty interesting. So this is what we're going to prove. The strategy is kind of always the same, right? So to prove that something is NP-complete, we're going to first note that 3SAT is in NP. You can either see it directly by saying, well, look, you give me a 3CNF and a candidate assignment, I can figure out whether the assignment is satisfiable or not efficiently. Or you can just note that, look, 3SAT is a subset of SAT, and I could already decide, I could already SAT itself was in NP, right? So it cannot be outside of NP. To show that it's NP hard, rather than, again, starting from all NP problems, it suffices to reduce from an NP-complete problem. So we will show that SAT can be reduced to 3SAT. Namely, given a subroutine that decides a decision problem for 3SAT, it is actually possible to solve the decision problem for SAT. It's generalization, like the satisfiability of any Boolean formula. Okay? We could have started from CSAT, but there is no point to start from CSAT. We already have an even simpler problem that looks closer to it. So generally, when you want to do reductions between problems, you want to start from problems that kind of look like them. It's a good heuristic to follow. All right, so let's do this. At a very high level, what we need to do is we're going to start with some, so we need to write a reduction, right? So we need a reduction, which means we have to pre-process and we also have to post-process. What does it mean? We have to, given a SAT instance, a formula, a general formula, we need to produce a 3SAT formula that sort of encodes within it the satisfiability of the original formula. So kind of let phi be a Boolean formula. We want to map, transform phi into, let's call it phi prime, into a 3CNF phi prime, such that phi is satisfiable if and only if phi prime is satisfiable. Okay? And we need the size of phi prime to be at most polynomial in the size of phi. What we'll actually achieve, we're going to have a quadratic blow-up, and that's polynomial. So this transformation has two steps. The first step is that we're going to transform phi into a CNF, just in conjunctive normal form. Okay, this just means an AND of ORs. Okay, and I'm not right now worried about how many literals there are in each OR clause. Just an AND of ORs. It's like a two-level formula. So it may look something like x1 or x2 or x3 or x5 bar or x7, and then end maybe x1 or x2 bar, and then blah, 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 right? So it's an AND of ORs. This step is actually somewhat non-trivial. We're going to do it using a recursive procedure. So we're going to, kind of a bit hard to see it directly, but the high-level idea, we're going to be using the Morgan's laws. Okay? And so what are the Morgan's laws? Remember that, an expression such as the negation of A and B is the same, logically the same as not A or not B, and the negation of A or B is the same as A and, so not A and not B. Okay, so these are De Morgan's laws. Roughly speaking, we're going to be using De Morgan's laws to take expressions like these and kind of push the negations down all the way to the bottom, because an expression of this sort doesn't really appear here, right? So all negations in a conjunctive normal form are at the bottom, okay? There's no negation up here, let's say, of this entire clause or across clauses. But there may be in a general Boolean formula. General Boolean formula is just this tree of AND order knots, and so it has multiple layers, and both ANDs and ORs are sort of alternating with knots. So we're going to take these negations and push them down to kind of squash the formula into this two layers. And one way to think about it is just recursively. So we're going to have a recursive algorithm A of phi. That would be the transformation for us. So we can just go case by case and analyze kind of what happens in each case. So first, let's think of the base cases, okay? If phi just looks like a literal xi, then we really have nothing to do. It's already in conjunctive number form. We're just going to return xi. If phi just is a negated variable, then again, we're going to return that negated variable. There's nothing to do. It's already in CNF form. If phi is a doubly negated variable, this may happen because we'll be pushing down negations, then we know that we just return xi. So these are kind of the base cases at the bottom of the recursion. Then we have the situation where we have a negation above an AND or a negation above an OR, and we want to kind of push it down. So if phi looks like some expression and some other expression, so it's some expression P and expression Q, and I have a negation above this expression, then we're going to return, we apply the Morgan's laws, and we return whatever A is going to do on not P or not Q. Okay? So again, A is going to do something, the right thing inductive, we're now defining A, right? We want to construct an A that will transform phi into CNF form. We've defined the base case. Now we're kind of doing the recursive part. Here, we know inductively that it's going to return the right thing. Okay, we're just going to push down a negation once. And similarly, if we have phi that is the negation of P or Q, then we're going to return A of not P and not Q. All right. So that was handling negations. Now we have to handle when we invoke this thing, this A is going to find itself doing something or something else, and we need to process it. Okay? So if phi looks like P and Q, okay, then this is kind of the easy of the two cases, because that's some expression, this is some other expression, they're smaller than the original expression. It suffices to transform each into CNF form and end it separately, right? Because this is going to be in CNF form, and if we end it with something else in CNF form, we get something that is in CNF form, okay? And the only case that is slightly non-trivial is the OR, right? Here we cannot just separately invoke A on P and A on Q and just AND the things together and OR the things together, because we're only allowed to put ANDs between them, okay? So instead, what we're going to do, we're going to first ask what A does on P individually, and what it's going to do, it's going to return to us the clauses of the CNF, okay? And it's going to return us, if we say, hey, A, here's an expression P, please turn it into CNF, it's going to return, what is a CNF? It's just a list of clauses that are ended together. So let's call them P1 through Pm, which kind of represent the expression P1 or up to Pn, okay? So when A squashes P, it squashes it down into M ended clauses, and each of these is a clause with ORs. We could also ask the same what A does on Q, and it returns some number of clauses. Okay, Q1 to Qn. Maybe some different n, right? And now we need to use these things and construct what we're going to return. So the idea here is that we're going to return this expression, a big AND of I equals 1 to n, and another n of j equals 1, sorry, I equals 1 to m, and j equals 1 to n, of the expression pi or qj. Let's think about why. So first, let's understand that this is indeed a CNF, right? So we have ends of things, okay, so that's fine. And then we need to make sure that these guys are OR clauses. Okay, if this is an OR clause and this is an OR clause, this is definitely an OR clause. But why are these individually OR clauses? Because they're the returning output of A on P, which is squashing it into like OR clauses. So syntactically, this is a CNF. Now, logically, why does it encode the same thing as P and Q? Well, this expression is true if either P or Q is true. Now, for either P or Q to be true, we need all of Pi or all of Qi to be true. And if that's the case, then certainly in each of these pairs, there will be some Pi, one of the Pi's or one of the Qj's is going to be true, so this entire expression is true. Now, conversely, the only way that this expression can be false is either P or Q is false. For that to be the case, it means that either among the Pi or among the Qj's, for this expression to be false, we need both P and Q to be false. So it means that both in the Pi and in the Qj, there is one I and one j where the expression is false. But look here. Here we have all combinations of I and j, and there will be one expression that is actually false, and because they're all ended together, the entire expression is false. So this means that this recursive algorithm constructs a CNF, and moreover, the CNF encodes the satisfiability of the original formula. We only have one more thing to check. We need to make sure that the CNF output by A is not too large. So let's see. Here we're the base case, and we're not doing really anything interesting. Here we're just kind of splitting it, combining it again, so we again have the same size. Here we're doing a recursive call on smaller instances that add up to the original instance, so again, nothing interesting is happening. But this part here looks like we are adding additional costs. In particular, here we're producing something whose size is m times n. But kind of the worst case here is when m equals n, and really this is like a quadratic blow-up, and you can analyze this using kind of the master theorem, and it's not hard to show that the size of a of phi is bounded by phi squared, order of phi squared. So that indeed, A returns a CNF that is only polynomially larger than the input general Boolean formula, and it encodes its own the satisfiability of the original Boolean formula. Okay, so this is the first step of like squashing general Boolean formula into CNF. But we need to do a little bit more. The definition of 3-sat requires phi to be not just a CNF, but to be a 3CNF, which means that each OR clause is allowed to contain a maximum of 3 literals. It's okay to have fewer literals. So for the second step, we're going to transform from CNF to 3CNF. This step is comparatively easier, and we're going to do so clause by clause. Right, so a CNF is an end of a bunch of OR clauses. Pick them one at a time, and let's just transform each one. So suppose that you have a clause that looks like x1 or x2 or x3 or x4 or x5. Okay, the negations and the exact names don't really matter. Let's just say we have 5 elements in an OR clause, 5 literals in an OR clause. We're going to introduce auxiliary variables. I'm going to chop down this clause into a collection of clauses that encodes the satisfiability of the original one. So here's how we're going to do it. You're going to say x1 or x2 or some auxiliary variable y1. And y1 bar or x3 or another auxiliary variable y2. Okay? And y2 bar or x4 or another auxiliary variable y3. And a y3 bar or x5. Okay? So we have mapped one clause into 4 clauses. Here was this was an OR clause with 5 literals. Now each of the new clauses are ANDed together. It's in 3CNF form. Okay? And we need to ensure that the satisfiability of this clause has been encoded correctly in the satisfiability of this collection of clauses. Let's see. Suppose x1, x2, up to x5 are all false. That is to say, this clause evaluates to false. Then we would like to say that no matter what the auxiliary variables do, this collection of clauses is unsatisfiable. Well, let's see. Because x1 and x2, so kind of the only way to satisfy the new clauses would be, okay, because x1 and x2 are false, we need to set y1 to be true. If we set y1 to be true, then y1 bar is false, and x3 is also false. So to make this clause satisfied, we need y2 to be false, to be true. So we set also y2 to be 1. Okay, now y2 bar is 0, x4 is false, so y3 has to be 1. But now we get stuck here, okay? That because y3 bar is 0 and x5 is 0, then it means that the last clause is not satisfied. So we know that there is no way, we just reason through it with constrained propagation, there is just no way for the collection of clauses to be satisfiable. Now conversely, suppose that one of the original literals is true here, so it means this entire clause evaluates to true. We need to show that there is a way to set the auxiliary variables to make this new collection of clauses satisfiable, to be satisfied. So suppose, for example, that x3 is set to true. Okay, just as an example. Okay, So the way we're going to reason, we're going to say, okay, x3 appears here. Now, because x3 is 1 already, I know that this clause is satisfied, no matter what y1 and y2 do. But my job is I need to make this clause satisfied, and this other clause satisfied. So here how we're going to do it. We're going to set auxiliary variables to the left. We're going to set them to be true. Okay, so the auxiliary variable to the left of x3, that's just y1. Okay, so we're going to set y1 to be true. Okay, so basically we're going to set previous auxiliary variables to 1, right? And the previous auxiliary variables in this example is just y1. And then we're going to set the subsequent auxiliary variables to false. Okay, so we're going to set y2 to false and y3 to false. Why? Because y2 bar is true and y3 bar is true. So we're going to set y2 and y3 to be 0. So that is the subsequent auxiliary variables are set to 0. Okay? Now, x3 was just an example. It could have been x2, x1, or x4, and x5. We can reason the same way. X whatever is going to be somewhere here. You focus in on wherever that x appears, and to the left you set things to be true, and to the right you set things to be false. And it's easy to see that no matter what you started from, this will make the new collection of clauses satisfiable. And you do this for every clause. These two transformations together transform a Boolean formula into a 3CNF. First you squash it to a CNF, and then you map each OR clause into a collection, an end of multiple 3CNF clauses this way. The second transformation increases the size of the formula only polynomially. So overall, the two transformations then taken together modify the formula at most polynomially. Oof. All right, this transformation is actually quite, let's say, non-trivial. In retrospect, it's clear why 3-sat is NP-complete, but sort of if you think about all the steps that we took to get here, first establishing a C-sat is NP-complete, then sat is NP-complete, then 3-sat is NP-complete. All these steps taken together would have been pretty hard to make in one step, but chopping it down into different problems along the way made it more tractable. And now we have this very cute and rather simple problem that is NP-complete. It's just an end of ORs, and each OR has 3 literals. That's a pretty simple kind of Boolean logic kind of question. And building off of this one, it will become rather easy or less hard to show that problems that don't have to do with Boolean logic are also NP-complete. Ones that a priori maybe you would surmise there is some good algorithm for. So that's what we're going to do now. We're going to pick some problem that has nothing to do with Boolean logic. I'm going to show that that problem is NP-complete by showing that it can be used to decide 3-sat. Okay? So we're going to study the problem of independent set. Okay? So the problem of independent set is the relation where your instance corresponds to a graph and an integer, and the witness corresponds to a independent set, okay, of a certain size. So S is an independent set in G of size small g. Okay? Just remember, what is an independent set? It is a set of vertices, set of pairwise, it's a set of vertices, no pair of which share an edge. Okay, so you put down all these vertices and no pair of them actually share an edge. So clearly, it is easy to come up with independent sets of small size. For example, the empty set is an independent set, or just a singleton is itself an independent set. But asking if there is a sufficiently large independent set, that may involve some algorithm. And we would like to understand the complexity of this problem, right? And so before these few lectures, if one were to ask you, okay, given a graph and a desired size, please find an independent set of a certain size, or decide if such a set exists, you may have been scratching your head for a long time to try to look for an algorithm. Maybe there is one. Maybe there is something smart one can do, maybe with divide and conquer or greedy. But now, with the language of reductions, we'll show that solving this problem is tantamount to solving 3-SAT, and therefore all of NP. And by establishing this connection, then you realize that there is no point to look for an algorithm of this sort for this problem, because it wouldn't imply an algorithm for 3-SAT, which we don't believe exists, an efficient algorithm for 3-SAT. So now we're going to prove that independent set is NP complete. So as always, you need to first establish that independent set is in NP. Let's just say why that is the case. If you give me an instance and a candidate solution, I can figure out efficiently whether this one is an independent set, because I can just, for every pair of vertices in the set, I can ask whether it is an edge in the graph. If so, then I say no. If not, I need to make sure the set has a certain size. If that's also the case, then I know that it is in the relation. So this is clearly an NP. For showing that it is NP hard, we're going to reduce from 3-SAT. We're going to show that 3-SAT reduces to independent set. Okay? So this is pretty interesting, right? So we have some combinatorial, some graph combinatorial problem, and we want to use it to solve a problem about Boolean logic. Okay? Apparently they look very different, but 3-SAT is also pretty simple. All we really need to reason about is satisfiability of 3CNF clauses. Okay? At a very high level, what we want to do is we want to design a graph such that finding independent sets of a certain size on this graph is tantamount to solving a question about a 3-SAT formula. So let's do it via an example. Okay? So suppose that our original 3-SAT formula is the following. Phi is x bar or y or z bar, and x or y bar or z, and x or y or z, and x or y bar. Okay, so there are 4 clauses in 3 variables. So we're going to transform this into a graph where at high level we're going to have a click on each clause. Okay? And then we're going to relate different clauses. So first let's just put down a click on each clause. So let's write it. So we're going to write node y, node x bar, node z bar. This is the click on the first clause. Why click? Because eventually what I'm really interested in for the satisfiability of this formula is I want to pick one element from each. I want to make each of these clauses satisfied. All I really need, I need to find one true variable in this 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 one. Okay? So I put down a click here. It means that it will never be the case that both this and this will be in some independent set because they share an edge. So here I'm saying pick one out of the three to make it true. So here I'm going to say again, node X, node Y bar, node Z. This is the clique for the second clause. The clique for the third clause. And the clique for the last clause, in this case is just two nodes. And notice I'm slightly abusing notation when I write, let's say, this node labeled Y and this node labeled Y, I'm labeling them the same, but they're actually different vertices. Here I mean a node that corresponds to the variable Y in this clause and a different node Y that corresponds to this variable Y in this other clause. Okay? All right, so that's a graph. And if I wanted to pick an independent set that has large size, I would have to pick one from here, one from here, one from here, one from here. But we still have a problem because it could be that so far, with the edges so far, an independent set would pick, say, this Y and this other Y. But really, they cannot both be true at the same time because Y is either 0 or is 1. So it cannot be that both Y and Y bar are true. So we can prevent that by putting an edge between them. If I put an edge between them, then it is not possible in the same independent set to contain both Y and Y bar. But look, there's more Ys and more Y bars, so I have to propagate the consistency between these. I have to say this Y bar and Y cannot be chosen together, neither can these two, nor can this one here, right? So now all possible, it is not possible with all the edges I've put down to pick both Y bar and Y. Okay, like only one of them can be true. I have to do something similar for the X's and the Z's. For example, X and X bar cannot be part of the same independent set, so I add an edge. That's true also for this X bar and this other X, this X bar and this X bar and this other X over here. Of course, notice it is okay to pick together both X bar and this other X bar. Indeed, there are no edges between them. And I'm left to make consistent choices on the Z's like this. Opa. Okay, so I've put down all of the edges for this construction. Notice that the transformation is efficient because for each clause I write down a clique of its size, and then I add edges. Okay, so there's at most quadratically many edges, so this clearly has polynomial size in the original formula. So now we need to kind of convince ourselves that this new construct encodes the like finding an independent set of a certain size here corresponds to solving the original formula. So here we constructed G. We still need to declare what is small g, the size of the desired independent set. So because there are 4 clauses, I'm going to put here 4 because I expect to make one choice per clause because all clauses need to be satisfied. So there are 2 kind of claims at high level that we want to make. So one is that if S is an independent set in G, capital G, of size small g, then there exists an assignment A such that phi of A equals 1. Okay? So the proof is that when we say G and this other G, we mean the ones that were constructed from phi, right? Not just arbitrary ones. Like it's important that this is the one that the reduction constructs. We're not saying that solving independent set on any graph has something to do with Boolean formulas. It says solving independent set on this specific graph built from that formula will mean solving the decision problem for this formula. So the way we're going to construct A is go as follows. Say, for each vertex V in S, for each vertex, V represents an assignment of some xi to 0 or 1. What do I mean by that? So I have an independent set, okay? Some sets are inside it, okay? I mean, some vertices are inside it. So go and figure out who they are. So if you picked this one, then set y to be 1. If you picked this one, then set z to be 0. If you picked this one, and set y to be 0, okay? So for each vertex independent set, the choice of the vertex in this graph represents an assignment of some variable to either 0 or 1. You're going to do set that variable accordingly. Note that you may not have assigned all variables with this process. Like it could be that here we picked let's say, y. What do I want to pick here? Let's say I picked y bar, and then inside here I need to pick, let's say, okay, here it doesn't show as much, but it could be that one independent set doesn't actually set all variables. Like some variables are left free. So we're going to say set the remaining variables arbitrarily. Okay? Now, because G, small g, is the number of clauses of phi, we know that all clauses are satisfied. Why? Because we have an independent set. We have made, there's one choice per click, okay? Also, it is not the case that both a variable and its negation can appear in an independent set. So we have set the variable without inconsistencies, and each clause is satisfied. We have made a choice here, a choice here, a choice here, a choice here, and each of them were built to represent a satisfiable choice without any, and there is no possibility for inconsistencies. Okay, so the way we construct this assignment is consistent and makes the formula satisfied. Now, for the other direction, we want to say that if A is a satisfying assignment, for phi, then there exists an independent set S of size small g in capital G. This is pretty easy to see because for any clause, pick a true literal and pick the corresponding vertex in the graph G. And because there are G clauses, then we have constructed an independent set of size G. So for example, in this formula, the assignment x equals 0, y equals 1, and z equals 1 is a satisfying assignment. Let's check that. If x is 0, this is satisfied, and this is satisfied. And because y equals 1, this is satisfied, and because z equals 1, this is satisfied. So all of them are satisfied. With this being the case, I can just say, well, because x is 0, I can pick this vertex and this vertex that makes these two satisfied. Because y is 1, I can pick this one, And because z equals 1, I can pick this one. So this choice of 4 vertices is an independent set of size 4 in this graph. Okay? All right. So what we've learned is that this problem about graphs may not be so easy after all, because if you want to solve it in its full generality, in particular, you have to solve instances of this form, but instances of this form encode within them the hardness of deciding 3-SAT formulas or 3CNF formulas. So we don't really expect to be able to solve this problem in its full generality, because along the way we would have to solve this problem. And to solve this problem, we have to solve SAT. To solve SAT, we have to solve CSAT. And to solve CSAT, we have to solve all of NP. Okay? So by way of example, we're going to sort of exercise sort of this kind of sort of establishing some problems in NP complete for a different graph problem. That again, a priori, seems like some cute graph problem that one can easily solve, but turns out to be not so. So we're going to be discussing Hamiltonian cycles. So the Ham cycle binary relation is as follows. So the instances is a graph G, and the witnesses is a cycle C, such that C is a cycle in G that visits each vertex exactly once. Okay, that's called a Hamiltonian cycle. Okay, so clearly you can always find a cycle, on a connected graph that will visit every vertices, but here we have this condition that you can only travel go through each vertex once. And we want to claim that Hamiltonian cycle, let's call it HC, is NP complete. So don't forget, the first thing you should try to check is that Hamiltonian cycle should be inside NP. Why is that the case? Well, if you do give me a graph and you give me a candidate Hamiltonian cycle, I can check first of all that it is a cycle. And secondly, I can efficiently just go through the cycle and make sure that it touches each vertex exactly once. So this is a condition that I can check efficiently. So this is definitely an NP. For NP hardness, it suffices to reduce from some NP complete problem. And here sometimes this is some art to picking the right NP complete problem. Here we're again going to use 3-SAT. But the answer is not always the case that you want to reduce from 3-SAT. But today it is going to be so. So we're going to show that it is possible kind of to program instances of Hamiltonian cycle so that finding a Hamiltonian cycle is tantamount to finding a satisfying assignment of a 3CNF formula. So, okay, so this is a very cute construction. So we're going to go through it. So we're going to construct a graph. So the graph is going to have two parts, some part 1 and part 2 of the graph. Part 1 is dedicated towards consistent variable assignments. So we're going to put down a graph that somehow traveling through it binds you to assigning to each variable either 1 or 0, but not both. Okay? So there's going to be some sort of starting vertex S. And what we're going to do is that we're going to have n layers. N layers, which corresponds to the number of variables. And in each layer, we're going to have m plus 1 vertices, where m is the number of clauses. Okay? So that's m plus 1 for now. Let's say it's 5. So let me make a little bit more space. So now I have to put down some edges to make this interesting. So intuitively, this m kind of hops between the m plus 1 vertices are going to each correspond to one of the clauses. And each of these is going to correspond to a variable. So this, for example, could be variable x1. This could be variable x2. This could be variable x3. And we're going to connect the starting vertex to the two endpoints of the first layer. This one corresponds to, let's say, assign x1 to be 1. And this one corresponds to assign x1 to be 0. And you can traverse each of these layers either left to right or right to left. See, if you start here, you must move this way. If you start here, you must move that way. And then you can move on to the next layer, either in the same direction or by switching directions. That would mean you assign x2 to be like something else. And again, for this layer, where you can either start from left or from the right, you continue this way, and at some point you exit from either the left-hand side of the last layer or the right-hand side of the last layer. You arrive to some vertex t, and then you make your way back. Okay? So somehow in this graph, what it's doing is that if you want to touch, now notice there are multiple cycles here. I could just travel like this, but I don't touch the other vertices. That's not a Hamiltonian cycle. So if you want to find the Hamiltonian cycle, you must touch all the vertices in a cycle that doesn't visit each vertex more than once, that visits each vertex exactly once. So the only way to do that here is that if you start here, you must go across. And if you go to the next layer, you either start from the left or the right, but you must go across in one of the two directions because you have to. That's the only opportunity to visit these vertices. So all Hamiltonian cycles on this part of the graph correspond to a value assignment to the variables. But so far, we haven't done anything about clauses. Okay? We also need to kind of put a part of the graph that has to do with clauses. So this part 2 is going to be kind of additional pieces that are added to this graph for each clause. So I'm going to say we're going to add a new vertex for each clause. So here it is. Here's the vertex. And here's some vertex for clause j, where j is between 1 and m. And let's say that for simplicity, we're discussing x1 or x2 or x3 bar. Okay, and you can generalize from here. Now, because we've made this vertex part of the graph, finding a Hamiltonian cycle means you must visit this one. Now we want to set up additional vertices from the main part of the graph so that visiting this one is tantamount to either picking x1 to be true, or px2 to be true, or x3 to be false. So one way to do that is we say, okay, let's look at the jth column here. Let's say that this is the jth column, that corresponding to the jth clause. And we're going to take vertices, we're going to connect vertices from this column to here in the direction. So in one direction, the one direction, if it appears unnegated, and in the zero direction, if it appears negated. Now, here we already have many arrows, so I'm going to just do the graph over here. So let's say we have x1, x2, and x3. And kind of from this graph, we have somewhere something that looks like this for each of these variables. Again, I'm just zooming in on, that's this, this, and this. They are this this part of the graph. I'm kind of zooming in it here. Here I want to say, okay, x1 appears unnegated. So traveling in this direction corresponds to picking x1 in this clause. So here's what I can do. I can connect it this way, because if I wanted to travel this direction, to go from here to here, I could just make a detour to visit this vertex and come back here and then continue that way. That is the same as saying I'm going to pick x1 to be true within this clause. x2, same thing. In the same direction, I can do it this way. x3, because it appears negated, we want to be traveling from this direction. So coming from this direction, it means I have to put an edge coming out this way and coming back the other way. So that the only way to visit this vertex is to commit yourself to assigning x1 or x2 to be 1 or x3 to be 0, which is tantamount to satisfying this clause. And I do this gadget for each of the clauses. So I do this, and for each clause, I'm individually using one of these columns so they don't interfere with one another. And that's how it works. So notice that the new graph is only polynomially larger than the original 3CNF formula, because how many vertices are there? Here there is m plus n, right? So there is m in each layer, n variables, or rather m plus 1 times n, plus 2, plus m. Okay, that's this order of m times n. So this is clearly a polynomial size relative to the original formula. And all these gadgets together encode kind of finding a Hamiltonian cycle in this instance of Hamiltonian cycle problem is tantamount to finding a satisfying assignment for the original formula. And this tells us that this problem is NP-complete. So pictorially, and I'm not going to argue this more precisely because I think the drawing is sort of clear enough. So pictorially, what we've done so far is that there is there's all of NP, and everything reduces to CSAT. CSAT reduces to SAT, which itself reduces to 3SAT. And now we have shown that 3SAT reduces to independent set and also reduces to Hamiltonian cycle. And whenever you come up with some other problem, I don't know, question mark, in NP, or let me call it A, in NP, and you're wondering, is it NP-complete? Now your strategy is that you can start from any of these, right? Maybe you're able to reduce directly from CSAT, or maybe from SAT, or maybe from Hamiltonian cycle. And when it has established to be NP-complete, the next problem B, you have even more options to start from. Okay, so there is this interconnected network of NP-complete problems that, as they get bigger and bigger, like establishing a new problem as NP-complete becomes sort of formally easier. Okay, but the point is that these reductions is a formalism that lets you establish the conjectured hardness of problems. Okay. Now, in the book, in the chapter about NP reductions, the book covers many more problems beyond the independent set and Hamiltonian cycle. It takes some time to get used to these reductions, so I encourage you to kind of go over them and see if you can come up with these gadgets yourself. There are design patterns to these gadgets, and so exercising to try to come up with these gadgets yourself, can be very helpful. Yeah.